Welcome back to Math on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. In the previous video, we actually proved L'Hopital's rule and did a couple of examples. Now we're going to pick up with just straight examples of L'Hopital's rule, and I tried to pick some problems that might be a little bit more on the challenging side, so hopefully you get some good practice here. Here's our limit that we want to evaluate. The limit as x goes to infinity of x squared plus e to the 4x divided by 2x minus e to the x. Alright, so it becomes pretty clear that if you just plug infinity into this, you will get infinity in the numerator, and then you'll basically just get some form of infinity in the denominator, because you'll have 2 to the infinity minus e to the infinity. Again, both top and bottom are infinity, so we have indeterminate forms, specifically of this kind, the second kind right here. So we're going to have to take derivatives. Let's do it. What is the derivative of the numerator x squared plus e to the 4x with respect to x? Well, the x squared part is just 2x, and e to the 4x, its derivative is just 4e to the 4x. Again, our derivative rules, so on and so forth. Okay. What about the denominator, 2x minus e to the x? Derivative of 2x is just 2. You might have seen a z there a minute ago. I fixed that. So it's just 2 minus e to the x. So the derivative of that is just minus e to the x. All right. So what happens if we plug infinity in here? We still have infinity in the top, and we basically have negative infinity in the denominator. But that's still infinity over infinity. So at this point, we are still in indeterminate form. So we have to do L'Hopital's rule a second time, which is what we're going to do down here. So, what's the derivative of the numerator now? 2x plus 4e to the 4x. Well, 2x's derivative is just 2, and then 4e to the 4x, its derivative is 16e to the 4x. What about the denominator, 2 minus e to the x? Well, the 2 is just a constant, so the derivative of the denominator is just negative e to the x. And what I'm going to do here, just to make this a little easier, I'm going to pull this negative sign from this e to the x right here out in front of the limit. So I have the negative limit as x goes to infinity of 2 plus 16 e to the 4x, all divided by e to the x. Okay? Now, it turns out that I'm actually going to be able to evaluate it here. It doesn't seem like it because I'll have an infinity up here and an infinity down here, but I can actually manipulate this algebraically to make this a little bit simpler. The reason I'll need to do that is because if I keep taking these derivatives, I'm just going to continue to have e to the x in both the numerator and denominator. That won't help me because we know that e to the x, when you differentiate it, you just get e back. So what I'm going to do is I'm actually going to distribute the e to the x in the denominator to both terms in the numerator. So I'll have the negative, here we go, limit as x goes to infinity. Now I'm just going to have the 2 over e to the x. That's my first term. Remember, I can break up limits like this. Plus the limit as x goes to infinity of the second part, 16 e to the 4x over e to the x. Okay? And again, I can simplify this a little bit more because now I can specifically take the second term right here and cancel the e to the x in the denominator. So I'll still have negative over all of this, limit as x goes to infinity of 2 over e to the x, plus the limit as x goes to infinity of 16e to the 3x. Now I can easily evaluate this. I just have it down here. If I let x go to infinity for this first limit, 2 over e to the x, what happens? Well, I'd essentially have 2 over e to the infinity, or 2 over infinity. That part's just 0, okay? But the second part, if I have the limit as x goes to infinity of 16e to the 3x, exponential functions like this, whenever the argument is positive, which it is, 3x, it's just going to blow up as x increases. So if I throw an infinity in here, this second limit is just going to go to infinity. So I have 0 plus infinity, the whole thing has a minus sign, and so the entire limit of this function as x goes to infinity is negative infinity. Now, in calculus terms, we would say that this limit diverges. So anytime a limit diverges, it means that the limit goes to either plus or minus infinity. So in this case, it goes to negative infinity. In the previous example, it went to 0, so we would say it converged. It went to an actual number that we can deal with, 0. In this case, this limit diverged. All right? So hopefully this limit made sense, let's actually do a second example in this video. This is overall example number 3. We're changing variables here, so now we're using t. Again, doesn't really matter. Here we have the limit as t goes to infinity of t times the natural log of 1 plus 3 over t. Alright, let's plug in infinity and just see what happens. Well, obviously this t is just going to be infinity. This natural log function, what's 1 plus 3 over infinity? Well, 3 over infinity is 0. 1 plus 0 is 0. And what's natural log of 1? 0. So we've got a problem. We don't have the explicit indeterminate form because we have infinity times 0. Now it turns out that if you ever have infinity times 0 or negative infinity times 0, that is also indeterminate form. And here's why. Here's my limit right here. I can actually pull this t into the denominator and show you its indeterminate form. The way I can do that is I can pull t into the denominator and make it 1 over t. So my limit is now t goes to infinity for natural log of 1 plus 3 over t divided by 1 over t. I did not change the value of this limit, but I did put it explicitly in indeterminate form, because now I have the numerator goes to 0, and now the denominator also goes to 0, because 1 over infinity is 0. I now have explicitly 0 over 0. Now I can apply L'Hopital's rule. And here's some some somewhat complicated derivatives, I guess you could say, but it's still very doable. Let's do the derivative of the numerator. Derivative of natural logs are just 1 over the argument of the log, so 1 plus 3 over t, times the derivative of the inside function of the log. So remember, 3 over t is the same as 3 times t to the negative first. So if we take the derivative of that, we would have negative 3 t to the negative second, or negative 3 over t squared. Okay? In the denominator, what's the derivative of 1 over t? It's just negative 1 over t squared. Okay, those are simple power rule derivatives in the denominator, and this one is a chain rule with a power rule. Alright, now I've got this, what can I do? Let me multiply both the top and bottom by t squared. Why do I do that? Well, first of all, these negative signs cancel in both the numerator and denominator, so it's still positive, but this t squared right here in the numerator cancels with the 3 over t squared, so there's no more t squareds, and then down here in the denominator, the t squared cancels with the 1 over t squared. So overall, all I'm left with is the limit as t goes to infinity of 3, which is still there, over 1 plus 3 over t. And now I can evaluate it because I can plug in infinity and I will no longer have indeterminate form. For the denominator, it would be 1 plus 3 over infinity, or 1 plus 0, or just 1. The numerator is just the numerator, so the entire limit boils down to 3 over 1, which is just 3. And unlike the previous example, where the limit diverged, this one actually converges to a nice value, 3. Alright, so this was another example of L'Hopital's rule. In the next video, we're going to cover some slightly more complicated L'Hopital's rule examples where we actually may have to do a substitution. And sometimes these kind of problems can crop up for teachers that aren't very nice. And then we're going to do, in the same video, another problem where we actually solve a limit and discover the definition of the exponential number e. Join us in that video, but please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.